Now we want to look at some analytical modeling of geological phenomena. In this demonstration, I will show you two phenomena and how analytically they can be looked into. The first thing that I want to show you is called Darcy's law, which is a groundwater flow between two along a hydraulic gradient. So I am going to essentially put in some values for the hydraulic gradient, the permittivity, the viscosity, the length, the pressure difference, and so on and so forth. And we can write a simple piece of code that represents Darcy's law and run that piece of code. But the problem with this is that this is division by 0 and we will get an error. So let us now write the code appropriately. There is a mistake here. This should be times multiplied by. So if I execute this code, I will get 0 because I've put in the pressure difference to be 0. Now, if we write this as a function, because I want to be able to change these values and look at the flux, the flow rate essentially. So I've written a little function, and then I can put in some standard values to look at that. And if I execute this function, then I still get 0 because I put the pressure difference as 0. Now, if we take an example, real life example, where we are using different values for the different parameters in metric system, obviously, the MK system is given on the right-hand side, but the values being used are shown in green. And then we can generate the flow rate. Now, one would be very interested in how if the length varies, how the flow varies. So the first thing we are going to do is create a range of values for the length of the aquifer. And we are saying that the length of the aquifer varies from 0.05 to 1. And we are going to look at how the flow rate varies every 0.005 meters. So this is the array telling you each individual distance points. And we are writing the same code, except we are now providing it for meter cubes per hour, the flow rate. And we can generate a plot of length versus Q. Okay. Now, this plot is not very useful because you don't know which units are in which axis. So here is the column, here is the figure that shows you the flow rate in the y-axis and the plug length of in the x-axis. Now, one question you might ask is, what if I want to see how this flow rate varies as I change the plug length, or sorry, how as the pressure difference varies? Okay, so in this particular case, we have accepted a particular dP value. Okay. So we can write a little code using this interact decorator, where I am going to change the pressure difference from 0, that is no pressure difference, to a pressure difference of 4 with an interim step of 0.1. So I can change the pressure difference by an interval of 0.1, and I can see how the flow rate will change for the different plug length values. And now I am going to run this piece of code. So let me run this piece of code. I believe that was already, oh, I didn't run this piece of code. So this was my practice. Okay. this, this, right. This, okay, so we have that. Then I can execute that. So now what we have here is something very interesting. We have an interactive graph where you have, for a pressure difference of a particular value, in this case, 2 megapascals, you have a plot of how the flow rate varies at different distances in the plug length. Now, if I make the plug, dP equal to 0 megapascals, obviously the plot vanishes, because if there is no pressure difference, nothing is happening, no flow is happening. Now, if I gradually move, if I change this value, you can see immediately the graph gets updated, where you can see what is the flow rate for at these different distances in the plug length. So if I continue to change this, so typically this is a little slow. If you make dashboards using either Dash or Streamlit, this becomes a little faster. Obviously, your computer also has to be a little fast. So next, you can see how you have a lot more control. Now, if you don't want a slider but a button to click, you can also do that. Again, that will be shown later. So you can actually see how this value, this graph changes with the pressure difference. So you can choose to compare different parameters as you wish. So that is how you can look at how Darcy's law can be analyzed. Switching subjects, let us go to structural geology. And what I want to show you is this Biot-Ramberg equation, where we are looking at how the viscosity difference between two rock units and their thicknesses affect the dominant wavelength. Most of you have heard that if we surround a competent or a strong unit with incompetent or weak units, the weak units merely flow away when this deformation is happening, as the strong unit controls everything. Now, the thickness of this strong unit also plays a role. And let me show you a simplified version of Biot-Ramberg's equation. So the first thing I'm going to show you what happens when you have a low viscosity medium enclosing, or that means you get short wavelengths. Short wavelength in low viscosity enclosing medium. That means the medium that is enclosed is strong and the surrounding material is weak, and you get short wavelengths, because what I just described, the strength of the competent unit or strong unit controls how the outer material behaves. However, if the viscosity or the strength of the material of the enclosing and the enclosed unit are close or almost similar, you can see large wavelengths. This is nothing, very complicated or rocket science. In fact, one of the arguments of Biot-Ramberg's equation, in fact, in the modified Ramberg equation, is that if the competency contrast is 1, or there is no difference, then all you get is just thickening. So the famous Biot-Ramberg equation is written in this particular manner, and I've written a function. I have taken some data where I have provided the thickness of the unit. Then I have put in the competent unit's viscosity, and then I have put in the surrounding rocks competence. So in a spreadsheet, I have a rock unit name, initial thickness in meters, the viscosity of the unit that is strong, and then the viscosity of, or rather the viscosity of the unit being enclosed, and the viscosity of the enclosing material. And I have this data set, so I'll run that. And then I will calculate the fold wavelength for each of those formations. So for example, for this unit, where I have a competent unit being enclosed by a less competent unit, I get a pretty big wavelength. Okay. For these values, so I can generate all these wavelength values. This is some issue with the formatting. So some of the issue values are over here. Now we can record these values into a spreadsheet. So next, that is what I have done. A spreadsheet is created, and then this spreadsheet is accepted into a pandas data frame, so as to show you the name of the formation and the wavelength we are getting. These are the exact values that we are getting for those wavelengths. Now what you can do is an analysis of the individual units and their wavelengths. Okay. Now we can give these stratigraphic units some color and make a nicer plot where you can see how different stratigraphic units have different wavelengths. Okay. Now you can look at the structural geology of an entire area and see which units influence what structure. So for example, obviously, this one has very low wavelength. Do you think this unit is going to influence the unit above or below, where they have very high wavelengths? So that is the structural analysis that you can do and actually match them with the field. So this is the end of this demonstration.